Right. Yeah, but I mean, so the size sort of do that as well, right? It's just, it's sort of nice to, I guess I'm just saying, like, the information you usually want, you could either take a known rho or psi and figure out what your operator is, or you could take a known operator and calculate the expectation value to figure out what the rho is. So generally, we know what the operator is, right? Like it's like IZ or IX, and we want to get information about psi, right? You see what I'm saying?
I don't think that is necessarily true. I think that really what this does for you is it provides you all the information about your states, about the size, right, without being involved at all with what you're trying to measure at the end. Like it doesn't matter what you want to measure at the end, as long as if you make sure that you're being consistent about following what's going on with rho, you will be able to at the end extract whatever observable you like.
Yeah, I'm just saying the expectation value itself, that's what you observe because there's an ensemble. And you make a measurement, your measurement is a measurement of expectation value. The expectation value is a function of your rho / psi and your A. And so generally we're looking at A. We know what A is and we want to know what rho is.
Right.
So the number can give us information about rho. There you could do it the other way, I guess. Yeah, it makes sense that you could do it either way.
Okay, and I guess now I would kind of ask you to maybe follow along with this proof here to make sure that you all understand how this proof works. I guess it's kind of nice because it uses, characteristics that Bertram just proved on the board, basically for alpha and beta, right? So you start out from here, which gives you how you calculate an expectation value, and then you insert this property, and the nice thing is you can insert identity basically always and wherever you want, because identity commutes with everything, so you can just put it, basically just throw it in an expression, whatever you like. So I guess this is kind of what's happening here. You start from here, and then here, between the psi and the A, so where I inserted it, I guess I inserted it here, right? You just throw in your basis states. Do you see that happening? Right? And then, always, this is also kind of nice, when you have your brackets closed, like this is an expression where your bracket is closed, and this is an expression where your bracket is closed, right? Then the nice thing is these are numbers, right? And numbers, you can basically always rearrange in whichever way you want. Does that make sense, Bertram? Mm-hmm. Right? So now you can basically take these and just switch them around, right? And this is what happens in this next step here, right? So you just switch them around because they're numbers, their order doesn't matter. And now you can see that basically what you have here is this kind of an expression where you have your basis vectors in the beginning and at the end, right? And if you have something like this, where you have a sum over that is enclosed by your basis vectors like such, that basically gives you your trace. Are you guys interested in proving that this is true, that this is the trace? I guess one can sort of do it with alpha and beta again, right? So, who volunteers? Yeah?
That's what I guess. So we have so we have alpha, and then rho A alpha plus beta, rho A beta. And that's what the sum is.
That's exactly what it is.
And then, so this is our matrix. Let's call it rho star or something. Rho star 1 1, rho star 1 2, rho star 2 1, rho star 2 2, you do the vectors.
Can we just for simplicity, make just one operator of this? Say we just leave A out or something like that?
Yeah, this one.
Yeah, okay,
this one, rho star equals that.
Yeah, okay. Oh, great, yeah.
And this one's 0, 1. This one's 0. But this one. Okay. Rho star, 2, rho star, 2, 1, rho star, 2, 2, 0, 1. And this is. It's roast 1, 1. No, that's 0, 0. That's right. And it's mess this up. It's supposed to be a number, isn't it, right?
In the end, yes. So you have a mistake here. The multiplication of the matrix by the line matrix should be line matrix.
Yeah, it's this one. It's this way, right?
No. No. Even so, you don't have a square matrix after making one product. You have either a column matrix or a line matrix.
I see what you're talking about. Right. So it's just this times this, and then this times this, right? So it's like 1, 1 star.
Right. Perfect.
That's how it works.
It's not 0 though. Doesn't matter.
No, it's not 0. It's row 1, 2. Row 1, 1 star, row 1, 2 star.
Right.
It does matter.
Well, ultimately it doesn't matter in the end.
Right, yeah, in the end it will turn into 0.
It matters in the ones for
Now it's row 2, 1 star, row 2, 2 star, 0, 1, and then that's, no, this one's row 1, 1 star, and this one is row 2, 2 star. Right. And then that's equal to the trace of row star. Perfect.
Does this all make sense?
Mm-hmm.
Yeah? Great. Okay, well, this is, I guess, a simple proof that we can calculate the expectation value of some observable just by doing this operation. And if you know draw, then it's reasonable. Okay. I guess here I come up with like an example to show how this would work, for instance, right? So say we have only alpha populated, and then basically our psi function looks like such: 1, 0, 1, 0. You calculate the density matrix, right? And you basically only have population here, and then say we want to measure how much is there in the coherence I minus. So and this is coherence here, right? And then basically all you need to do is calculate the trace. I guess I should have switched these around, right? This is actually kind of important, I guess, that the order is correct, that it's always first row.
No, I don't think it matters. I think in a trace,
Oh, you're right.
it's you can switch for.
Right, okay. So then basically you check how much of the coherence I minus you have in your density matrix row. And you perform whatever the math, and you get the result 0. And that basically just only if you have a state alpha, which is just some population of one of the states, then there's basically nothing in this corner of the matrix. And basically that's all you're doing when you're examining some expectation value here in this case.